Okay, so we're going to make a start because it's past now. So welcome everyone. It's good to see we've got over 200 people for our event tonight. My name is Dr. Andrew Tickle. I'm the IT Coventry and Warwickshire Secretary. I'm also a former chair of the network and also a former Young Professionals chair as well. So it's my great honour to present to you Dr. Peter James. He's going to be doing our talk tonight. So it's going to be on electric vehicle evolution and the challenges of green transport. So again, the event is going to be recorded and it will also be put on the IETYP's YouTube channel, and the link will be distributed after the event, after I've had a chance to edit everything together. So once Peter's finished presenting, then you can put either your questions in the chat, or you can unmute your microphone and ask them yourself. So it's going to be a really good event tonight. Again, as we are recording, if you can keep your microphones off while Peter's presenting, that would be great. And I will now pass over to you, Peter. So over to you, sir.
Thank you very much. So good evening, everybody. Thank you very much for joining. Hopefully you'll find this interesting and thought-provoking presentation. As Andrew said, I'm Dr. Pete James. I work for Lyra Electronics, and Lyra specialize in power electronics, mainly for transport systems. So not only electric vehicles, passenger vehicles, but also marine, aerospace, and rail. So let's get on, move forwards. Just 1 second. There we go. So the agenda this evening is a quick overview of electric vehicles, the requirements of electric vehicles. So, put into perspective really what we are talking about, how they work, charging systems that are currently available, and then future technologies. So it's really an overview of where we're at with electric vehicles currently in the world, and what are the future technologies that are being worked on and where they could possibly help. So my name's Pete James. I'm Director and Technical Specialist at Lyra Electronics, but I'm quite involved in the IET. I used to chair the ART TN, so that's one of the technical networks, and ART stands for Automotive and Road Transport Systems. So we cover automotive, so heavy truck, light commercial and passenger vehicles, and then all the road transport systems, so road charging, highways, all the sort of things that are based around the road system. I'm currently the chair of the PEMD TN. So this is the power electronics, machines and drives. So what we're interested in there is anything to do with power electronics, motors, and the drive electronics for the motors. I also sit on the IET Transport Policy Panel, where we advise the government on transport policies, and I'm there really to help with the charging infrastructure in the UK, electric vehicles in the UK, and new technologies around batteries, power electronics and motors. And also for the IET, I sit on the committees that author the code of practice for the EV charging point installation. So it's very similar to the wiring regulations, but specifically for EV charging points. So both the high energy, high power charging points, as well as the lower powers as well, and also the code of practice for energy storage systems. So if you have any solar PV and you've got energy storage in the home, these are the sort of rules and regulations that need to be met. So where are we at the moment? Battery electric vehicles in the UK. I checked today, as of the end of last year, we have 164,100 in the UK. So these aren't hybrids. These aren't mild hybrids or plug-in hybrids. These are pure electric vehicles. And the SMMT are suggesting that there are over 5,000 new registrations per month. So, you know, it's really taking off now, and there are a lot of these vehicles about. And what's good is that there are over 30,000 public charging points. So a lot of the charging points have two connectors. So this includes all the connectors that we currently have in the UK. So what do we have with the electric powertrain? What you see on the right there is essentially the powertrain for a Jaguar I-Pace. It has a motor at the front on the left-hand side, and it has a motor on the rear over the two axles. And we have the batteries as a sort of skateboard underneath the passenger compartment. This keeps the weight very low and gives the vehicle good stability. So the three things that make up an electrical powertrain are the energy source, the batteries, the energy controller, which controls the power, the electricity from the batteries into the electric motor, and the energy converter I've put there, which is the electric motor. And I say energy converter because that's what we're doing. We're converting electrical energy into kinetic energy to move the vehicle. So if you look at the requirements, we'll whiz through these, some maths there. Losses mainly due to aerodynamics. If we look at something like the Tesla Model S and we do the maths, we come out with around 10 kilowatts is required to keep the Model S running at 70 miles an hour. If we look at the rolling resistance, then we're looking at in the tires probably around something like 300 odd watts per tire, and that gives us 1,300 roughly for the whole vehicle. So this is also at 70 miles an hour. So in total we're moving, around probably about 12 kilowatts is needed to keep the vehicle moving, something like a Model S moving at 70 miles an hour. So that's our constant power requirement, but our maximum power requirement, so this is for acceleration. If we want to, for example, accelerate up to 60 miles an hour in 5 seconds, which a lot of the electric vehicles do, if the vehicle weighs 2.2 tons, we need about 12 kilonewtons. And if we work out the distance covered, we can work out the energy and then the power. And it looks like there we need about 170 kilowatts. And it's not surprising that this is the sort of power output that these vehicles have. The Tesla and the I-Pace have considerably more than this and can move considerably quicker. So as I said, the total power for 70 miles an hour, around 20 kilowatts. And I've put twice this in reality. And this is due to atmospheric conditions, temperature, air density, all sorts of things that you actually, that affects the rolling resistance and drag. And then if we look mileage on the motorway with a 60 kilowatt hour battery, so if the vehicle has 60 kilowatts and we're consuming around 12 kilowatt hours, that means we can run for about 5 hours. And if we're doing 70 miles an hour, we theoretically can do 350 miles. Now, what we actually know is that in reality, these vehicles, if you take something like the 60 kilowatt hour Nissan Leaf, it does about half 350 miles, so around 175 miles on a charge. So if we look at the batteries, the most widely used battery in electric vehicles today is the lithium-ion battery. And not all lithium-ion batteries are the same. At the last count, there were over 600 different types of lithium-ion battery. Sometimes they're called lithium polymer batteries. The most common by far is the lithium cobalt oxide battery. We find that in our laptops and our mobile phones. It's the most energy dense. but it's also the most volatile and unsafe. The lithium iron phosphate battery is in a few electric vehicles, but it doesn't have the energy density, both for weight or size, that the others have. There, the cobalt oxide and the manganese oxide. So the lithium ion isn't that popular, but by far the most popular in electric vehicles is the lithium manganese oxide battery. And when you're sizing these batteries for vehicles, this is just a quick excerpt from an Excel spreadsheet I had from a company called Melasta, who make lithium-ion batteries. And they do 490 different types of battery. They're all essentially the same chemistry, but the geometry of the battery means that it has different discharge rates, different capacities, and therefore it has different uses. This, what you'll find is that when we're talking about these batteries, the C rating is key. And what the C rating means is the amount of energy we can take out of the cell given its capacity. So it's a sort of rate function that tells you how quickly you can discharge the cell. So if, for example, you take the top one, it's only a 230 milliamp hour cell, but you can take the energy out at 20 C. And what this is actually meaning is that if you were to run the battery for an hour, you could actually you would take 230 milliamps out of it for an hour. If you're running at 20 C, then you would empty it in a 20th of the time, but you would be able to take out 20 times the current in that time. And so it's all a juggle between power and capacity. Again, you know, there are different types of lithium-ion battery. There's also different constructions. We have cylindrical cells. These are often found in laptop computers, and it's what Tesla use in their vehicles. Which is essentially a set of plates which make up the battery, and they are rolled up like a Swiss roll into a cylinder. We have prismatic cells and pouch cells where the plates are actually stacked up together. The prismatic ones, they're stacked up into a sort of cuboid case, which is usually fairly hard. And the pouch cells are stacked up into what essentially is a bag. This is the process of the anode and cathode creation of a battery. It's extremely involved process. The material that actually makes up the anodes and the cathodes is mixed together, the active materials. The plates are coated and compressed to get as much on there and to control the thickness. It's then dried because it's a sort of liquid slurry that's actually created. And then the plates are actually cut to the correct size for whatever type of battery they're manufacturing. Then the actual cell has to be assembled. And this is the process of the cell assembly. And you can have a look back on the video at this, but again, it's an extremely laborious process that takes a considerable amount of time. And I'd like to draw your attention to the formation, which is 4 from the bottom in that flow chart on the right. And it takes 30 days to actually form the SEI. And the SEI is the I'm trying to think now, sorry, something electrolyte interphase. But it's essentially the insulation bit that separates the two halves of the cell, and it's where the ions actually flow through, and the electrons can't flow through this particular part of the battery, and the electrons have to flow around the electric circuit through the anode and cathode. And so this takes 30 days, and it's a constant charge and discharge cycles to create this layer. And so it's very energy intensive and very time consuming. As I said before, there's many different battery cells. And so we have to put some in parallel and some in series to increase the current handling or the power that you can get out the cell, and we put some in series to increase the voltage and again increase the power. So it's a huge combination of series and parallel. And I think off the top of my head, something like a Model S Tesla has around 7,000 battery cells in a combination of parallel and series. So there's an example there. If we were to have 108 in series and 15 in parallel, then we could achieve a 90 kilowatt hour battery, so very similar to the Tesla and the iPace, and we'd be able to achieve 270 kilowatts peak, which is around 675 amps. But this is actually distributed across 15 parallel cells and 108. The voltage is across 108 in series. So the battery management system is included within the battery on the vehicles. Not all the cells are the same. So this is due to manufacturing tolerances, purity of the electrolyte, resistance to the electrodes, and simply the temperature of the cells. Some cells could be hotter than others. And the manufacturing processes over the years have got much better, and so the top three are greatly improved, but there is always a management system on board, and the management system is trying to keep the lithium-ion batteries safe. So it's looking at undercharge, overcharge, over temperature, manufacturing defects, and shorted cells. It's constantly monitoring the system, and what it's trying to do is an incredibly complicated problem. And you can see in the center of that slide, you've got the battery monitoring unit, and it's looking at the battery state of charge model, which is constantly comparing what the battery is doing to an ideal battery and trying to predict what the energy storage and the capacity left on the battery is. And all these systems are to keep the battery and the pack, and so all these batteries together as the pack, in this safety window, which I will just show you. It usually ends up in thermal runaway, and you've probably heard about some instances where the batteries on these vehicles have caught fire. But it's no worse than having a petrol engine or diesel and the petrol catching fire. These batteries are very, very safe in their normal operation, but the computer and the systems on board do have to keep them safe. And this system's running all the time, even when the car's switched off. This is constantly monitoring the cells. And during charging, the batteries have to be balanced. And so what this means is that due to tolerances, and as I said before, the temperature and so on of the cell, each cell charges up very slightly differently. And so we have this balancing system, which is usually passive, in that energy is actually wasted as heat from each of the cells. As one cell gets a little high, the energy is bypassed via a resistor, so it doesn't flow into the cell, it flows back through the resistor, and the others then can actually come up to the same level, and this optimizes the battery. And if you have one of these electric vehicles, what you'll notice is that the battery pack can be charged really quite quickly, up to maybe 80 or 90% state of charge. But when it starts getting very full and very close to 100%, then the speed in which it charges backs off. And you can often have this cell balancing phase, which can last up to an hour. depending on the vehicle and how out of balance the cells are. And the car really doesn't know this until it actually gets very close to full. And I've noticed in mine that, you know, I can get to sort of 99% and it'll tell me there's only 10 minutes left. And then 10 minutes later, it's still telling me there's 10 minutes left. And it's doing this balancing. And it's the computers aren't quite sure how much balancing is required, and it just has to wait until all the cells have caught up. But what it's essentially doing is optimizing the amount of energy stored in your battery and keeping your battery in optimum condition. So if we look at some of the motor technologies, going back to the early days, the brushed DC motor. I don't know of any electric vehicles currently with brushed DC motors, but the principle of the motor is quite simple. We have a coil on a rotor, which is the item that rotates, and we have stationary magnets, and the coil current is passed through the coil via brushes that rub against a commutator. If you can see, my pointer is just here. And then these coils here induce a magnetic field in the rotor, and this opposes or attracts the magnetic field in the magnets. And so the motor turns. What we have today is in many of our vehicles are brushless DC motors. And this is where the coils are actually on the stator. So the coils don't move, but the magnet does, and the magnet is on the rotor. And this makes this removes the need for the brushes, which are an item that wear out, and it gives the motor a much higher reliability. But what it means is that the stator has to create a rotating magnetic field in synchronization with the rotor in order to make the motor spin. And we'll see a bit later with our motor drives how this works. An induction motor, very similar in that you have a rotor and a stator. But the rotor doesn't have any magnets on it. The rotor has windings, more copper windings where current can flow, but the current is induced by the stator. So what has to happen is that you create a magnetic field with the coils on the stator. This induces a magnetic field in the rotor, and this in turn creates a current in the rotor. And then the computer controlling the motor has to change the magnetic field in the stator to oppose the magnetic field that's in the rotor. And this keeps happening very quickly, and so the motor turns. And this is an induction machine. It has the advantage that it doesn't use any magnets, so it's a lower cost. But because there's a lot more copper in there, and they're not quite as efficient because it's having to induce its own magnetic field, it makes the motor a little bit bigger, a little bit heavier, and so it's not that useful, or it's not been widely adopted by electric car manufacturers. We have the switch reluctance, which is a very interesting motor, where again, we don't have any magnets, but also we don't have any copper in the rotor. And so the rotor is just made up of the iron core of the motor. And what you're trying to do here is you're trying to align magnetic fields. So if you can see my pointer here, from the stator, a magnetic field is created, and it comes out of this lobe of the stator, and it tries to go into the rotor and round and back out again. And the rotor tries to align itself to optimize the magnetic flux. What the computer then does is it changes the magnetic field in the stator, and this then causes the rotor to move to realign. And if you do this quick enough and synchronization with the rotor, you get a spinning motor. And you can see on the right, this is a reel in switch reluctance machine, and it's rather pretty. The rotor is there, and the shape of those curves in the actual rotor's iron represent the flux of the magnetic field, and the magnetic field flows through those. quite efficiently. The problem with the switch reluctance machine is that it has a very high torque ripple, which essentially means that when the rotor is aligned with the stator, there's a massive magnetic flux flow, and the rotor is very well held against the stator, so it's very strong. But when it's not aligned, it's very weak, and so you keep getting these ripples of strong, weak, and that in turn, when it's transferred through the drive line, the gearbox, and so on down to your wheels, it actually results in audible noise, which is not that pleasant for the driver. But there's a lot of work going on to change the way in which switch reluctance are manufactured and controlled. So there are ways in which they can be controlled using the different software and different configurations of the motor drive, which minimizes this torque ripple. So have a quick look at what these look like in real life. This is a Nissan Leaf motor. It only weighs 42 kilos and produces just over 100 brake horsepower, so the equivalent of 80 kilowatts. And this is a what can be called a pancake motor. The technical term is an axial flux motor, and these are very, very power dense. So as you can see, this is producing 100 kilowatts peak power, so more than the Nissan Leaf motor, and almost half its weight, and an incredible amount of torque. They're very, very strong. They're often used as hub motors, but they're very costly. The manufacturing methods of this motor mean it's quite a costly machine to manufacture. This here is the torque speed efficiency curve of the Oxford Yasser motor when it first came out. And as you can see, they're very, very efficient machines. The majority of that graph there is over 90% efficient. And so the motors themselves are really, really very efficient. And that's one of the big attractions of electric vehicles. So motors require, most motors require three-phase supply. And if you're familiar with three-phase supply in industrial applications for the grid, you have three sine waves. So you have three wires connecting your mains appliance or your electric motor. Each wire is a different phase, and each has a sinusoidal wave of current flowing through it, and these are 120 degrees out of phase with each other, and thus that gives us a fairly constant power for the electric motor. How we actually do this is that what you see on the left there is the rotor spinning between two magnets. Usually the magnets are on the rotor and the coils are stationary, but just makes it a little easier to visualize if it's the other way around. And as you can imagine, as that is spinning in the center, it describes a sine wave, which you can see on the right. So as theta moves round its 2 pi or 360 degrees, you can see the sine wave being created. And that sine wave is essentially the magnetic flux. It can be the magnetic force, and it's what we have to create using our motor drive inverter. And so there you have the rotor in the center. You can see the various positions of it, and the resulting wave at the bottom is what the motor is wanting at each point of the rotor, which is what we have to control. So we do this through what I call a motor drive inverter. Some people call them motor controllers. Some people call them motor drives. Some people just call them inverters. But what they're essentially doing is they're converting DC from the battery into AC to drive the motor. So in fact, when you hear about DC motors, no motor is ever DC. Every motor is AC. Even brushed DC motors are AC. because the brushes and the commutator actually convert it into AC. So what we're trying to do here is convert the DC from the batteries into AC. And we do this with a bridge of 6 transistors. So you can see there the DC supply, which is our battery here, and we have our 3-phase bridge here, and we have the load, which are the 3 windings on the electric motor. And so if you imagine the current is flowing out here, it goes through this leg, if this one's on, into the load here, through this winding, out of this winding, for example, and down here if this transistor's on. If this transistor was on, then it would flow this way. And what we do is the computer in the motor controller controls this bridge to control the current in the motor. And transistors are most efficient when they're either on, completely on, or completely off. And so we generate a sine wave using pulse width modulation. And what this basically means is that when the sine wave is at its lowest point, our transistor is on for the shortest amount of time. And when the sine wave is at the highest point, the transistor's on at the longest time. And the same for the bottom transistors to create the bottom part of the sine wave. And that is what it looks like generating a 3-phase sine wave with PWM. It's very difficult to see on probably your screens, but these traces are full of differing duty cycles, from very small duty cycle to very large duty cycle, to represent the sine wave. And this is how the motor inverters work. This is the sort of topology of a motor drive. We have essentially our electricity going in here from our battery. We have some reservoir capacitors here, some which provide sort of very localized pulsing of electric current for the IGBTs, which are the transistors that are commonly used in most of our electric vehicles to date. And these are the connections then that go out through the current sensors and out to our electric motor. The IGBTs, the transistors themselves, get warm, and so the whole of the bottom of this is a cold plate, which has liquid coolant running through it, which is usually an ethylene glycol mix, very similar to what we have in our engines, and that flows around cooling it. So the losses in the inverter are due to conduction and switching losses. And so what we mean by the conduction losses is just simply passing electric current through these transistors. The electric current flows from the collector through here, through to the emitter. It wastes energy. There's a resistance there to the flow, and the transistor gets hot. But we also have switching losses, and as this transistor comes on and off, you can see here, it doesn't do it instantaneously. So the voltage doesn't switch off in instant, and the current doesn't come on in instant. And during this time, it's what we call the switching pulse, and the transistors get hot due to the switching pulse. As I said before, the cooling is usually a water glycol mix. We have these fancy galleries where the coolant runs. This is actually the CAD for the heatsink you saw before. And as you can see, there's these little pins which sit in the liquid. And what these do is they help the liquid mix, and they also transmit the heat from the bottom of the transistor into the coolant and give optimum heat transfer into the coolant. As you can see there, it says it's only required under the semiconductors. So here's where our capacitors were, and here's where our current sensors and our output is. And really the only components that's getting warm are the semiconductors, or the transistors. Now, the software inside the inverters is incredibly complicated, and there's some amazing maths that go on inside these things. And one of the ways in which the motor is controlled is called field-oriented control. And what we're trying to do here is create a magnetic field with the stator. So those are the coils that are around the motor. We're trying to create a magnetic field in the shape of a sine wave, which is in synchronization with the magnetic field on the rotor, and creating a force vector between the two. And so what we have to do is we have to synthesize a current in a stationary object, and create a rotating magnetic field in the stationary object, which is slightly ahead or behind the rotor, and that will then either accelerate the motor or decelerate the motor, and thus give you either acceleration or deceleration of your electric vehicle. And we could have a presentation just on this that could last a couple of hours, because there's a lot of really clever maths going on here, and it produces a very effective result, which looks a bit like that, where we have the stator and rotor flux very slightly out of phase with each other. So what we're seeing across the bottom is time, and you can see that they're very slightly out of phase time-wise. And what this actually means is that when one is leading the other, we're actually getting force being put into the rotor, and so that's actually accelerating you. Or if they're lagging, we're taking energy out of the rotor and decelerating it, and that's where you're decelerating. And this is how we can use the electric motors to regenerate the electricity from your braking force. Now, one of the key things you'll probably noticed is that it's extremely important to know exactly where the rotor is, where those magnets are on the rotor, so that the magnetic field in the stator can be aligned correctly. And this is done with a sensor called a resolver, and these are usually rotary transformers which have a frequency going into them. And as you can see, there's here we have a frequency coming in on a coil of wire, and then we have two coils which are pickup coils, and these are 90 degrees apart. And so one is giving you a sine of the theta, in other words, the angle of the rotor. One's giving a sine of that, and the other one's giving a cosine of it. And the computer inside the inverter uses the sine and the cosine to calculate the absolute position of the rotor, and then it can synthesize a sine wave to suit. This is what one looks like in real life. This is one of our 150 kilowatt inverters. It runs at 450 volts peak, 375 amps, and is around 98% efficient. So have a quick look at charging systems. There's a quite a large array of charging systems out there. The main AC charging systems are mode 1 to mode 3. The mode 1 is essentially a standard plug cable and socket. So if you've seen these connections which plug into your vehicle, and you can plug your vehicle into a normal 13 amp wall socket, these are mode 1. Mode 2 has a standard cable, which I think is limited to about 16 amps, and it was common on the original Leaf. Mode 3 is by far the most popular, which is it's two flavors: the single phase at 7 kilowatts and 3 phase at 22. And then mode 4 is DC only, and I put there up to 93 kilowatts. This was the case a few years ago. We've gone a much higher than this now, but it requires a dedicated charger. It says there, of course, typical charging time 20 minutes, but you can be quicker depending upon what the size of your vehicle is. So if we look at the type 1 and type 2 and 3, so each of the modes have different types of connectors. We have the type 1 connector, as I said, used on the original Leaf. And then we have the type 2, which is more widely used now with pretty much all vehicles using the Mechanis type 2 connector. These are different types of connectors for high power systems. So we have the CHAdeMO on the left here, which is a DC connection, mainly used on Japanese vehicles, including the Leaf. We have in the center here the CCS, the Combined Charging System cable, which is again a DC. But this actually is essentially, the top of it here is the type 2 connector with some of the pins missing, and then the bottom has an extra DC connection. And then, and this is adopted mostly in Europe. And this one on the right here is, I believe, what the Renault Zoe uses, which is an AC charging connection. I won't go into too much detail here, but the charging connector that we use, which is the Mechanis type 2 charging connector, it has some little magic inside, which revolves around resistors, which dictate the current charging capacity of the outlet. So when you plug your electric vehicle into a charging point, the electric vehicle can measure these resistances here, and it knows how much energy it can actually pull from the charger. And what the charging vehicle does is it can actually send information back to the charging point using other resistors, and says it's ready for charging, and so on. So those, again, are the two rapid charging methods. As I said, the one on the left is adopted by the Japanese vehicle manufacturers. On the right are the European ones. We did a project a few years ago where we did a rapid charger for a charging point company, and I just thought it was quite interesting to show you just how many standards there are that you have to meet when doing one of these rapid charging. So the ones in the middle circle represent the standards for the connector. Then we have standards for the communication protocol, then the charging topology, safety on the right, and interoperability across the various vehicles on the left. And it's an absolute nightmare to adhere to all these, and many of the charging points don't actually adhere to all these standards. So it is possible that you can actually rock up with your electric vehicle to a charging point and find that it doesn't actually work and it's not supported by that charging point. The combined charging system is quite interesting because it uses essentially an Ethernet protocol, a TCP/IP protocol, to communicate between the electric vehicle and the charging point. And the reason for doing this is that in the future, we can have smart charging stations where the electric vehicle could essentially communicate across the power lines all the way through to the smart grid. And so the energy supplier or the national grid can actually have control over when your vehicle is charging and how much energy it charges, or even they could ask the vehicle to give energy back into the system and actually power the grid to provide grid support. So it's not used at the moment. The communications are only between the vehicle and the charging station, but it's all there ready to communicate all the way through to the grid back end. So that's an overview of the communication system. As I said, it's quite complicated. The AC charging that we see on the lower charging points is a lot simpler, but the communications for the high power charging is quite involved and quite challenging for the electric vehicles. Sorry. And this is inside one of the chargers. So this is the Dbt Charger from France. You'll see these a lot at motorway service stations. They're installed by Ecotricity. It's quite a popular one. This is a 50 kilowatt charger. As you can see, there's a lot of electronics inside these things, and they're very, very complicated. And generally speaking, most of the chargers are quite reliable. Now, there was a lot of teething trouble in the early days, but a lot of these have been sorted out now. So if we look at some of the future technologies that we might find on electric vehicles in the future, one of the big things that people are looking at, of course, are batteries. And this is a type of battery called a flow battery, or sometimes it's called a redox battery. That's the process that goes on for the energy storage. And this battery has quite a big advantage in that the actual energy is stored in a liquid electrolyte here and here. And so what you could theoretically do is you could visit a fueling station, and you could have the spent electrolyte pumped out of your vehicle and fresh electrolyte, charged electrolyte, put into your electric vehicle. And there's a lot of advantages with this, because the system and the pumps and everything are already there for us, the infrastructure. But one of the problems with flow batteries is these tanks are quite large to get any appreciable sort of energy storage, and the system in the middle is very similar to a fuel cell, in that the actual power density of the cell stack here isn't that good. And so usually the vehicles have to have another energy storage medium on there, like batteries or supercapacitors. But we do have a high energy density, and so something like this might find its way onto a heavy goods vehicle, or a marine, a ship or something like that, or a train, where size and weight isn't really an issue. Solid state batteries are really I suppose the holy grail of what people are trying to go for now. When we looked at the battery technology earlier in the presentation, it's the lithium ion we have today is like a paste. It's essentially a liquid electrolyte, and these solid state batteries have a solid energy storage electrolyte in them, usually a ceramic based electrolyte, and they're offering huge energy densities, and this is why a lot of the work is going on now. So 2.5 times the energy density. We're starting to get to the point where it's close to the energy density, relatively speaking, of petrol. So I'm not saying it is the energy density of petrol, but when you look at how much more efficient a electric vehicle is to an internal combustion engine vehicle, then the amount of energy you could store in the same space as, say, 60 litres of petrol with solid state batteries starts to become an option. The current issues at the moment, the severe losses in these cells getting energy in and out, and the ceramics that they use are quite fragile, and quite a high pressure is needed. So there's some mechanical and manufacturing techniques that need to be sorted before these will be in mass production in our electric vehicles. And then still, there's the lithium-ion battery is still got a lot of mileage in it. There's a lot of work going on here. And lithium air is, again, one of the holy grails of batteries. If you remember in your physics lesson, in your chemistry lessons, lithium is quite a reactive metal. And so a lithium air battery does pack a lot of energy density. As I said, they're very high, third of gasoline. But its stability is very difficult to control, and so actually to control this oxidization process and control the energy release is a big challenge. But there's a lot of people working on lithium air batteries. And to give you an idea of where the batteries sort of sit in the grand scheme of things, the internal combustion engine there, do look at the bottom scale. It's not linear. It's fairly linear up to 1,000 watt hours per litre. But then the last little bit is up to 10,000. So it's another order of magnitude up at the end of the scale. And we have the internal combustion engine, of course, up there. We've been very fortunate in being able to store a lot of energy in our IC engine vehicles. And if you look at where our current lithium-ion battery technology is, it's way down on this chart. Research is a little higher, but we have this Sakaki battery named after the founder of Toyota Motor Company, and he sort of predicted this holy grail of batteries, which, if I get my facts right, it's sort of about 2.7 megawatt hours in sort of 220 liters, weighing 280 kilos. If I'm right. So this is the ultimate in battery, where he feels, the level should be in the future. But if you look here about the lithium air's got really good potential. The target is here, and we're not too far off our internal combustion engine. On the side of the power electronics, silicon carbide a few years ago was very much in the future. It's now with us. To my knowledge, currently the only production vehicle on the road with silicon carbide is, I think, the Tesla Model 3, although the Porsche Taycan may well have silicon carbide in it, as it's an 800 volt system. And I think the Audi e-tron GT, their new sports car, also is silicon carbide based. Silicon carbide is essentially a new substrate, a new semiconductor, not using silicon itself, but a silicon carbide structure. And what this does is it has a high breakdown field strength, and this means that we can run much higher voltages. So we can get the power advantage with just increasing the voltage, but also the substance has very high thermal conductivity, and this allows us to run the devices much hotter, and therefore we can run the units much more efficiently and make them smaller and lighter. Gallium nitride is hot on the heels of silicon carbide. It's a little further away, although at the moment we're seeing 600 volt devices appearing, and so systems, things like the onboard chargers and things like that will probably be using gallium nitride very soon. They switch very, very fast. We're talking sort of a few hundred picoseconds switching speed. They've got very high electron mobility, so that means we can move a lot of current through them, and so they offer a very high increase in power density. But with this very fast switching and very high power density, thermal issues become a problem. We have to get the heat out of them, and also with the very fast switching speeds, EMC, so electromagnetic emissions are a problem, and so they can interfere with other systems on the vehicle or systems around. So there's a lot of work going on to control these things and try and manage them. Also in power electronics, we have strange things like silicon on sapphire, where silicon is deposited on a sapphire substrate, and that has advantages for temperature. I suppose the holy grail again for power electronics is diamond substrates, but you can imagine all the difficulties with diamond, just actually manufacturing the things and creating diamond slices is very difficult, but the structure of diamond lends itself to a very, very efficient and fast transistor. But additive manufacturing is also very interesting in the power electronics. What you have on the right is an additive manufactured heatsink, which is very, very optimal for weight and size. And so we can get very, very good transfer of heat from the device, which would be at the bottom of this image, through to the coolant, which could be flowing through it, or air. Very good transfer through heat sinks made with additive manufacturing. Future technologies on the charging point. This is me actually in our works Leaf, charging up at a Polar, which is ChargeMaster charging station in Basildon. I was thrilled to be able to try out their 175 kilowatt charger with my Leaf, which allegedly can do 100 kilowatts. And you may or may not be surprised to note that it didn't charge anywhere near as fast as that. And it probably didn't do much more than 50, which was fairly standard. I'm not sure why. Could have been the temperature, could have been the voltage at the time. But just to give you a quick overview of what we've got here, this is the charging point. There's very little electronics in there. There's probably just a few relays to switch on and off the current. Over here, if you can see these cream-coloured, beige-coloured cabinets, there's 3 because there are 3 charging points, and each of these has all the electronics for the charger in there. And then behind it, we have the 2 substations, which is taking energy off the grid. So this is a hell of an installation to provide 375 kilowatt charging points. But already we have 350 kilowatt chargers becoming available. People are manufacturing those, and we at Lyra Electronics are developing a 500 kilowatt charger, which we're actually looking at using a battery assist system, where you would have batteries in, say, one of these containers here, and the batteries could be charged up relatively slowly overnight, for example, or during the day. And then the electric vehicle can be charged up very, very rapidly, 500 kilowatts. So we're talking about 9 minutes for a Tesla Model S to get 300 miles. So quite doable, really. And I think that would be quite usable. We have fuel cells. So Toyota, being a world leader in this activity, have launched the Mirai, which is a fuel cell vehicle. It has a very small battery on board because the fuel cell can't react very quickly to changes in energy demand. So when you're accelerating or decelerating, you're using the battery, and the fuel cell fills in for your steady state. It has a 122 litre hydrogen tank, which stores 5 kilos of hydrogen at 700 bar. There are 2 standards for hydrogen, 350 bar and 700 bar. But to give you an idea that hydrogen fuel cells are very inefficient. And this particular vehicle has a 27 kilowatt air compressor. And so when the fuel cell is running at 114 kilowatts power output, 27 kilowatts of that is actually being used to blow air into the fuel cell. But even so, you know, the hydrogen, very clean, very easy to transport, very easy to, or relatively easy to store and charge the vehicle with. And it gives this vehicle 312-mile range. So that finishes off the presentation. I just wanted to finish on some future events from the technical networks that I'm working on. So please do join the ARTS or the PMD technical networks. You can go to the IET website and see these and join in the conversation there. The ARTS TN has events on vehicle and grid. This is a fantastic event that we ran in Coventry a couple of years ago, and we're hoping to run again when we're allowed to meet face to face, where we get the electric vehicle manufacturers, the OEMs, and we get people from the grid. So National Grid and Western Power and people like that, the distributors, and get them all in the room to chat about what the other means to them. And it's very interesting to hear the differences there. We also have a very successful electrification in motorsport. So motorsport's a very good area in which electric vehicles are being trialed and new systems are being developed. And then in general, running a decarbonisation in transport set of webinars, which you may be interested in, with the energy sector at the IET as well. So looking at really how do we reduce the carbon footprint of transport in general. So if you're interested in rail and marine and aerospace, as well as automotive, it covers energy and decarbonisation across all of those. On the power electronics, machines and drives, we've got a webinar series on high frequency switching. So if you remember me talking about silicon carbide and the gallium nitride, it enables us to switch much higher frequencies, but there are knock-on effects with the motors, the electrical machines, and so this is talking about how we mitigate those and how we can be mindful of them. And of course, the IET runs the biannual conference. The next one's in April 2022. Huge conference, very well attended, all about power electronics and motors, with a big sort of influence and concentration on electric vehicles. So I've spoken for pretty much 60 minutes. I hope you're all still there. You found it interesting, and I'm happy to answer any questions.
Yeah, thank you very much, Peter. There has been quite a lot of questions in the chat, so I said I would read them on a first come first served basis. So I hope this wasn't relating to any slides, but we're showing at the time the question was asked. But the first one was, how similar is battery technology to the one onboard electric aircraft? Regional or urban mobility?
To my knowledge, it's very, very similar. The aircraft have requirements for weight and more so than passenger vehicles, but generally speaking, these systems are very similar. But I think if I'm right in saying the sort of material, the chemistry of the lithium-ion batteries on aircraft is the lithium iron oxide, which are the more power dense or energy dense cells.
Okay, thank you. So the next question I can see is, how much energy in kilowatt hours does it take to manufacture a 100 kilowatt hour battery, and how much energy to mine and produce materials?
That's a very, very good question, and I have to confess I don't know the answer. It's a considerable amount, and it's an interesting thing really for me, because my company revolves around electrification in all aspects, and trying to reduce the amount of energy that's being used by all our systems. We're constantly trying to make things more efficient, and in doing so we use energy. My company uses energy to develop these things, and in the manufacture of the systems, you use energy. And so maybe the right thing to do is to buy an old petrol car that's 25 years old, didn't use very much energy at all in its manufacture, because there's very little technology on it, and it was very crudely made, so to speak, and run it for 100 years. And maybe the sort of cost of ownership energy wise for that vehicle is the lowest you'll find of any vehicle. But we have to look forward and try and reduce the energy consumption sort of today of what we're using. And I think electrification is the right way forward. But I think when we're evaluating the systems on the vehicles, we do need to be mindful of the energy required to manufacture these things. And one thing springs to mind, the BMW, when they were developing the i3, they developed a vehicle there which was quite quirky, and it was groundbreaking in many, many ways. And I don't think it got the right appreciation from the world, really, in that what BMW did was they said, well, we're going to make a vehicle and we're going to make it light so it doesn't actually use much energy. The manufacturing processes and the production lines and everything else, we're going to power off wind farms. So they actually built wind farms to power their manufacturing plants. And so really the i3 is a truly low carbon vehicle, but incredibly costly to develop and manufacture, which is a shame, really, because you know, for what electric vehicles stand for, the i3 was everything you could sort of wish for an electric vehicle, being you know, good for the planet and green. So yes, I mean, it's a very interesting question, and I don't know the answer to it, but it's a lot of energy.
Okay, thank you, Pete. So the next question is, to what extent is active cell balancing used in cars now, if at all?
To be honest, I don't actually know. My gut feel is that active cell balancing is too expensive for electric vehicles to date. In our experience at Lyra, active cell balancing really comes into its own when you have very large cells with very high capacities in the cells, because any percentage difference in tolerance between one cell and the next results in a bigger change in your pack. And so it's more common on the larger cells, which really are found more on buses and trucks. And so I think if it is being used today, that's where it'll be, in the larger battery packs and the larger battery cells.
Okay, thank you. But this isn't a question, but it's about the slides, but it's a question like, will you be able to share the slides after the seminar, webinar?
I don't see why not. If you can, do you have the means to distribute them?
Derek will have the list from the Eventbrite, so he should be able to distribute them. But yeah.
Okay.
So that should be a problem.
Yeah, we'll also be doing that with the video.
Okay.
Yeah. Yeah. So next question is, with only electric and electronic components in BEV, how are the challenges faced due to EMC emissions, electromagnetic compatibility, dealt with? And are there any change in industry standards from current petrol or diesel vehicles?
Excellent question. In my experience, the standards are just getting tighter, both for EMC and safety. So with it seemed to me that with petrol and diesel vehicles, the standards were quite strict. A lot of OEMs had different standards, but these have been tightened up with electric vehicles, and with the power electronics in there and the motors and that, it's a much more of a challenge than with internal combustion engines. Even, I mean, you know, spark plugs and that are notoriously noisy, EMC wise, but the power electronics are too. And so a lot of work goes on in optimizing the power electronics and trying to control the EMC. If anything, I would say that it's stricter now than it was with ICE vehicles.
Okay, thank you. So next question I've got is, what regulation is there to ensure transparency of life cycle embodied energy and also system operational efficiency?
Again, in my experience, I would have said none. There's no standards out there. It's, you know, we have a new sort of energy consumption gauge, which I can't remember what it is now, the WTL or something, which is the drive cycle at which these vehicles are gauged over. But it's very difficult to actually know, what's good and what's bad from one vehicle to the next, because the drive cycles and the way the vehicle is optimized for those drive cycles is it doesn't just, it doesn't carry from one vehicle manufacturer or one powertrain to another. And so it is very, very difficult, and nobody really quotes the efficiency of the system. And so, the battery chargers on vehicles are probably 92, maybe 92% efficient at the moment. The batteries themselves get warm, so they might be about 96, 98% efficient. The electric motors are 98. The power electronics can be anything from late 80s up to mid 90s. And it's very difficult to actually know where all these are. And then, of course, you've got, the biggest, as you saw at the very, very beginning of the presentation, the biggest energy consumption really is the aerodynamics. And this, is affected massively from one vehicle to the next. So, like our petrol and diesel vehicles, it is very different from one vehicle to the to another. So there's really no standards out there, to my knowledge, that the powertrain actually has to comply with or publish.
Okay, thank you. Quite an interesting question next. I'm just going to read this straight from the chat feed. So it said, great content, thank you. Personally, the battery charging time is a big issue, as it must be for many people. I can't accept the hype from industry, just have a cup of coffee when you recharge. And they said, is there any real prospect to get to the present energy recharge times per petrol / diesel, i.e. 5 to 10 minutes to get a 350-mile range? And when will this be possible? Thank you very much.
Right, okay. I think, to be honest, I think it will be possible at some point. I wouldn't like to say when. There's two problems here. There's the battery itself, or the energy storage of the vehicle, to actually get those number of electrons into the vehicle in that short amount of time. And then there's where you're getting the electrons from. And that's why at Lyra we're quite keen to have a very large, what we call dumb battery, because it doesn't put the stress on the grid. There are other people working on medium voltage chargers where you've got 0.5 megawatt at 33,000 volts, so it comes straight off the medium grid through a power converter straight into your vehicle, and you can get then 0.5 megawatt fairly easily off the medium voltage grid. Again, though, the grid doesn't like these sharp rises in energy demand. They like everything to be very steady. Their power stations are generating a very steady power. And if you've got a lot of electric vehicles randomly charging at very high rates, it can be problematic for them. And again, the battery idea sort of tries to smooth that out a bit. But I think the vehicle industry, the OEMs are moving to 800 volts, which essentially for their batteries, which essentially doubles the speed in which you can charge them by simply doubling the voltage. I think that's going to go up with silicon carbide being able to do 1,700 volts. We're going to see charging systems at 1,500 volts, I would imagine, and batteries running there. So, we're going to go half as much again. As I said, our 500 kilowatt charger should do 300 miles in about 9 minutes. So it's not too bad. But, when I'm traveling in my electric vehicle, I do have to plan. You can't rush anywhere. And you do have to plan your stops accordingly. And sometimes it doesn't matter. Sometimes it's a complete pain. And I wish I could just recharge with a petrol pump. but I think it will happen.
Okay, thank you. So the next question I've got is, in your governmental consultation role, what emphasis being placed on standardizing charging connectors? And there's been a few questions asked about that.
Yeah, it's a good question, and it's a real bugbear of mine. You know, owning an electric vehicle and rocking up to a charger and find it doesn't fit. You know, it doesn't really happen with petrol and diesel cars, does it? You know, you can charge those up anywhere. I have to say, really, the government aren't really particularly interested. They think that the market will sort themselves out. So I think the general consensus is that the combined charging system, the CCS, will prevail over all the others. It also, you know, it raises the cost of the chargers as well, having to put two connectors on there at least. And I mean, I can give you an idea that the CHAdeMO connector on a fast charger with its cable is about £800. So, you know, it's a large, you know, the charger itself might be 15,000, £20,000. And it's a lot of money in just the cables going to it. You know, nearly 10% of the cost of the charger is actually in the connector, and something does need to be done. I think moving forward, the CCS and the CHAdeMO aren't going to do the 500 kilowatts. There are charging connectors out there at the moment which have coolant running through them, so the actual connector and the cable is actually being actively cooled for the 350 kilowatt chargers. And I think that there will be a need for a different connector in the future, and I'm hoping that that will be a standard then that everybody will adopt.
Can I just interject and say that Peter actually has got something else he needs to do at 8 o'clock. So if we could just take a last one or two questions, and perhaps Peter could look at the questions and answer them with an email, which I will put on the local website.
Yeah, because we've still got quite a lot more with them, and they're coming in, and they're still coming in as well. Like I said, I said I'd go with them. I'll see if I can pick out some of the.
Can we just take two more?
Yeah. So I guess one question that is how many years will the battery last?
Back in the early days when the Leaf came out, people were thinking that the batteries wouldn't really last much more than 5 or 7 years. But you know, now that we've had the Nissan Leaf out there since 2011, I think we've got a lot of really good data back from those vehicles and how well the lithium-ion batteries have been lasting, and they're holding up much better than people think. And so you know, a lot of the OEMs now are guaranteeing the batteries for 8 years or more, 10 years. So I think, you know, realistically, you can definitely get 10 years out of them. But I would add at this point that the OEMs think that the battery is still fine when it's up to 70% of its capacity. So you just imagine that over the years, your petrol tank or your diesel tank starts getting smaller and smaller and smaller. And after 10 years, it's only 70% the size it was when you bought the vehicle. So it's a little bit difficult to comprehend, really. But that's what they're saying. They're saying the batteries will last 10 years. And the word last means, you know, still have 70% of their original capacity.
Okay, so I've picked two last questions out from the thing, which I think are things that people want to know. First one is, how do vehicles tolerate driving through floods, particularly like with a recent weather we've had recently? So 350 to 400 volts, the batteries are sealed, presumably.
Yes, they are. And all the connections are sealed. So all the wires to the power distribution units, the motor drive inverters and the motors, they're all very well sealed. And in fact, I do know that something like the iPace, for example, has a wading depth of nearly 2 feet. So it can go through really quite deep water, and the batteries on these vehicles are really low down, so they have to be kept very well sealed, and it does make them very, very good for going through water and floods and that sort of thing, much better than a internal combustion engine, which could breathe in water, and then you get hydraulic locking of the engine and a lot of damage. So generally speaking, much better than the IC engines.
Brilliant. And again, kind of following kind of similar question to that is, how do car batteries behave in various severities of crash, and what are the failure states and how dangerous are those states?
Okay, so there's a massive safety program that has to take place when one of these batteries is actually designed, and crash is a massive part of that. And so a lot of these batteries are actually segmented into modules with firewalls between them. So one of the problems is that if one cell gets ruptured, it can catch on fire, but that temperature rise and the fire causes the next cell adjacent to it to catch fire, and so on. And then the whole battery starts burning. And one of the difficulties with lithium-ion batteries and putting lithium-ion battery fires and putting them out is that the fuel and the oxygen to keep the fire going is all in the battery. And so you can literally put the thing in a vacuum and it would still burn. So the only way really is to either let the fire burn and remove all the fuel, so it burns itself out, or reduce its temperature. And so the recommendations to the fire service is, fill the battery with as much water as you can. And given what I said about the floods, that's actually quite difficult to do, to get the temperature down. But essentially what the OEMs do is they segregate the cells into small groups, so that if there is a fire, it's only a small fire which can be contained within the battery. And although it's devastating for the vehicle, it makes the vehicle very safe, and the fire of the batteries is not an issue.
Okay, thank you very much. I've copied the chat, so I'll get that sent across. So hopefully we might be able to get some more questions answered. There's been a lot of messages saying thank you for a very good presentation tonight, and I would mirror that those comments. So again, thank you very much, Pete, for turning up tonight, giving us this very interesting Zoom call, and I'm glad everyone's enjoyed it as well. So yeah, so thank you.
No, thank you very much, and I appreciate everybody attending and listening. And always very happy to do these events, and with my arts hat on, if we want to do a local event and maybe have a bit of a debate, get people involved, just asking a lot of questions and getting some other people from industry, maybe somebody from batteries and somebody from motors and so on. Very happy to arrange that, and I think the audience might be very interested in that. So in the feedback, if you want to see whether you'd like the sound of that, I can talk to yourself, Andrew, and Derek, and we'll see if we can pull something together.
One other question for Derek from a committee point of view is, we've had quite a few comments about, can we do CPD credits for this seminar tonight?
Yes, indeed, I can organise that.
Brilliant.
Yeah, basically I could. The problem is we don't have a list of those who attended. We have a list of those who registered, but not those who actually attended. So if you want something from the CPD, please email me. So it's derek.willer@ietvolunteer.org. derek.willer@ietvolunteer.org.
I'll put that in the video when I edit it as well.
Thank you so much. Yeah, and I'll put the video up online by the sort of this time next week. It'll be there, probably earlier than that.